Okay, so this up here is the gamma function's Weierstrass definition that we went over, and we actually used quite a lot. So yeah, we're going to use this to help us derive a new function, which is the derivative of the log gamma function. Now, we call this function the digamma function, okay? We notate it using the Greek letter psi. And I'll say we have argument z. Then this right here, you would first take the logarithm of the gamma function, so you get log gamma of z, and then just take its derivative. So this is just the logarithmic derivative of the gamma function, this right here. Now, that seems like a weird combination, right? But in fact, it's very nice in a lot of ways. Okay, another way you can rewrite this, actually, is just as gamma prime over gamma itself. Now, if you know anything about differentiating logarithms, right, take the derivative of log of just any function u, right, and say it's a function of z, then what you would get is, well, you want to put this guy, when you take the derivative of a log, you take the inside, put it in the denominator. So you have u in the denominator. And then by chain rule, you need to multiply by this guy's derivative, right? The inside's derivative, which is just u prime. So by this exact chain of reasoning, we get that the digamma function is just gamma prime over gamma. So now we're finally get to explore like some of the derivatives of the gamma function. But not quite yet, because we need a better way to write this, right? Notice that because you take a logarithm, it's really hard to work out using the integral definition of the gamma function. And you're also dividing by gamma itself. So you have like a log integral divided by another integral. That's kind of weird to work with. Let's find another definition, and we're going to start using this right here, the product definition. And why are we doing that? Well, because the first step here is just to take the logarithm of the gamma function. If you take the logarithm of a product, it breaks up into sums. So that makes it easier for us to work with. So let's go ahead and try that. Okay, so first step is just going to be take the logarithm of this guy right here. Okay, on the left-hand side, we get log of gamma of z. Okay, and then on the right-hand side, when you take the log of this massive product, it breaks up into sums. So let's go ahead and do that, okay? Take the log of, let's work with this product first. Take the log of e to the negative gamma z, okay? The log and this e are going to cancel out. It's going to leave you with this negative gamma z. So you're going to have a negative gamma z. Okay, you have the z in the denominator, so you're subtracting the logarithm of z. And then you have this product out here. Now, when you have, once again, when you have the log of a product, you can take the log of the individual factors and then just add them up, okay? So the same deal applies up here with this product right here. If you have the log of a product of, numbers, whatever, you can break it up into the sum, right, of the logarithms. So that's exactly what we're going to do here. If we take the log of this product, we can just turn that into the sum, and over the same index as well, of n equals 1 up to infinity, and then the logarithm we move to the inside. So I'm just going to write this down for now to avoid too much complication. Yes, like this. Okay, so hopefully that's legible. We can simplify this a little bit more, obviously. Okay, on the inside right here, what's going on is, well, you have a log of another product basically, right? Or like a quotient. On the inside of the sum, we're going to split this up into two. So we have log of the numerator minus log of the denominator. So the denominator is 1 plus z over n. Okay, this log and this e are going to cancel. You're going to be left with z over n for this first term. And the second term is not going to simplify anymore. So if we want to rewrite this, we can just go ahead and write negative gamma z minus the logarithm of z. And then we have this sum. I'm going to just write n is greater or equal to 1, okay, because that's what this is. Then the inside breaks down into, first we have a z over n, and then a negative logarithm of 1 plus z over n. Okay, nice. So there's one more thing we have to do before we get to the digamma function, which is just take the derivative. When we take the derivative on the left-hand side, we get obviously just the digamma function of z. Okay, how about on the right-hand side? Well, let's take the derivative with respect to z here. Taking the derivative of this term with respect to z gives you just negative gamma, because this is a constant times the variable, right? Okay, next. Negative log z. Well, log z, when you take the derivative, is just 1 over z. That's pretty simple. Okay, here in this sum, you can move the derivative inside of the sum, and then just take the derivative inside. Now, what does that look like? Okay, well, the sum's going to index the same. When you take the derivative of this first term right here, it's just a constant, which is 1 over n times z. When you take the derivative, you're just going to get 1 over n. This logarithm right here is a little bit more complicated. Maybe we can do some rewriting in here. Okay, so, well, let's work on this. So let's write this, let's rewrite this logarithm. 1 plus z over n. Okay, first thing we know is that this negative on the side, we can move into the exponent of the inside. So that's going to give us log of, well, the reciprocal of this right here. So that's going to be 1 over 1 plus z over n. Okay. Then expanding the numerator and denominator both by n, we're going to get log of 1 times n is n. And then this guy down here, well, multiply 1 by n, you also get n. Multiply this z over n by n, that cancels out, you get a z. So that's nice. And then you can break this up into 2. You have log of n on top. So you have positive log n, and then you subtract off log of n plus z, because it's in the denominator, so it gets subtracted. Okay, so this is exactly what's going on right here. When you take its derivative with respect to z, okay, the logarithm of n is just a constant, so it's going to go to 0. What you're left with here is, well, okay, basically just take the derivative of the second term. Okay, the negative is going to stay. The derivative of logarithm is just 1 over the inside, so 1 over n plus z. And then chain rule, you multiply by the derivative of the inside with respect to z. When you take the derivative of the inside, you just get 1. So that works for us right now. And right, there you go. This is a very nice form for the digamma function, okay, but it can be simplified a little bit more, although this is one of the closed forms if you want to use it. Okay, so I'm going to box this, and then we can revisit this later if we want to find another closed form. Okay, so I just copied down our results up here in black, okay, because we're going to be coming back to it later. Now, I want to figure out another property of the digamma function, and that's its recursive property. And to do that, we're going to use the gamma function's recursive property. Now, because it looks like the factorial function, in like video 1 of this series, we found that gamma of z plus 1 is just z times gamma of z. It's a very simple functional equation, but it allows us to do a lot of things. Now, how do we translate this into the digamma function? Well, once again, just like before, when we have gamma functions and we want to turn to the digamma function, we first take the logarithm, so you get a bunch of log gammas, and then you take the derivative. So let's do that. Taking the log on both sides, you get log gamma z plus 1. And on the right-hand side, log of a product is just going to be, well, a sum of the logs. So you're going to take the log of z first, and then you're going to add it with the log of the other factor, which is gamma of z. Okay, so now we have everything in terms of logarithms. We can very nicely just take the derivative now, right? Once you take the derivative of the left-hand side, the derivative of log gamma is just the digamma function, okay? And now the inside is going to be z plus 1. And then you want to do chain rule, except the derivative of the inside is just 1, so it's not going to affect this. This term right here, the derivative of log z just becomes 1 over z. And then the derivative of log gamma z is just, well, obviously digamma of z, right, by definition, as we found earlier. So right here you see that, well, we have this a functional equation for the digamma function, okay? So yeah, now we can actually go ahead and apply this to this, definition that we found earlier. So I'm going to copy, actually I'm not going to. So let's go ahead and try to apply this up here and see if we can simplify this definition anymore. Now, what I'm going to do from here is move this 1 over z over. Because you notice what happens is, well, now you get digamma of z plus 1 over z, which is what you have on the right-hand side here, and you can simplify that into this. So I'm going to just copy down again, okay, digamma of z, move this 1 over z over, so you get plus 1 over z. Okay, and then I'm going to copy down the rest. Okay, so yeah, this right here, as we found earlier, is just the digamma function of z plus 1. So we have a shifted argument here. Now, we want this defined explicitly in terms of z, not z plus 1. So what we're going to do here is we're going to just make a quick variable shift, okay? Wherever you see a z plus 1, you plug in a z. All right, I think that should be pretty obvious. So here we have a z plus 1, we're going to plug in a z. Okay, and on the right-hand side, what we're going to do is, well, we have negative gamma plus the sum, okay, n greater or equal to 1. Now, inside of here, the 1 over n stays the same, but here we have a z in the denominator, and we have to apply that shift. Okay, so originally, if you had a z plus 1, you make it a z. And that means if you just subtract 1 from both sides, you get z goes to z minus 1. So here you have a z, just plug in a z minus 1. So you get minus 1 over n plus, and then here, instead of a z, we have z minus 1. All right, and this is almost simplified, but this z minus 1, you can kind of group the negative 1 with the n. We can go ahead and just re-index the summand right here. So now let's do something similar to this. We're going to take n minus 1 and just map it to n. And there we go. So that is the definition of the digamma function I use the most, okay? And I'm going to be using the most in the next few videos where I talk about this function a little bit more, the trigamma function, and some other cool stuff involving this. So this is important to remember. This is the sum definition of the digamma function. Now, let's go back and revisit the digamma function's recursive property. And I erased it, but it's just this right here. So we have digamma of z plus 1 is equal to 1 over z plus digamma of z. Well, let's find a starting point, okay? Maybe z equals to 1. Let's start at z equals to 1. We can use this definition right here. When we have z equals to 1, so that's digamma of 1, then this sum, notice it collapses to 0 because you have 1 over n plus 1 minus 1 over n plus 1. Okay, so this sum is going to go to 0. So digamma of 1 is just this starting term right here, the negative gamma. So digamma of 1 is just negative gamma. All right, and from here, we can if you want to find digamma of 2, you can plug it in here. And I think it will telescope, but it's easier to just use this right here. Okay, and also, if you use this guy right here, it gives you a really nice pattern. Plug in 1 into here, you get digamma of 1 plus 1, so that's digamma of 2 is equal to 1 over 1 plus your starting value, which is digamma of 1, which is just negative gamma. So here, this guy becomes 1, right? That's 1 over 1. And then this term right here, digamma of 1 was just negative gamma right here, or negative Euler-Mascheroni constant. Okay, and then we can continue this. So digamma of 3, how would we find that? Well, plug a 2 into all of these z's up here. So on the left-hand side, you get digamma of 2 plus 1, which is 3. Here you get 1 over z, that becomes 1 over 2. Okay, and then plus the digamma of 2, which is 1 minus gamma. So plus 1 minus gamma. And if you keep going, you would find that digamma of 4 is just 1/3 plus 1/2 plus 1 minus the Euler-Mascheroni constant. And you can see a pattern emerging, right? This, for each term you increase, you get one more term of the harmonic series. So the harmonic series, if you remember, is defined as this. So say we have h sub k. This is just 1 plus 1 over 2 plus 1 over 3, and then dot, 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 until you get to 1 over k. And notice that that's almost what's happening here. It's just a couple differences. First of all, this digamma function has this negative Euler-Mascheroni constant hanging out the side. And then also the input is shifted by 1. So if you have digamma of 4, you're going to get h of 3 minus gamma. So notice that this right here, digamma of 4, is just h sub 3, because that's 1 plus 1 over 2 plus 1 over 3. So I'm going to write that in. And then minus the Euler-Mascheroni constant. So we can generalize this actually. This input is always going to be 1 bigger than that right there. So we could just say that digamma of k plus 1 is equal to the kth harmonic number minus this constant that's always there, this Euler-Mascheroni constant, and that's around 0.577, I'm pretty sure. So yeah, we just found a few pretty nice conclusions today. First, the digamma function is actually connected to the harmonic numbers. Okay, second, we found an explicit definition for the digamma function in terms of the sum, and we also, found out how to derive that, which I don't see covered a lot on the internet. And then finally, we found the digamma function's recursive property, which is right here.